Hi, everyone. Thank you all for attending today's webinar, Industrial Networks, the Choices for Real-Time Motion Control. We would like to thank our presenters for being here today and their respective companies. Joey Stubbs, he's a North American representative of the Ethercat Technology Group, and Sean Kneller, he's Key Accounts Manager at B&R Industrial Automation. So right now I'm going to introduce our first speaker. My name is Leslie Langnaw. I'm Managing Editor for Design World Magazine, and I'm the moderator today. Joey Stubbs has a Bachelor of Science degree in Electrical Engineering from the University of South Carolina, as well as several technical degrees and over 25 years of experience in the area of industrial automation. Sean Keller is a graduate of Brighton Technical College and Brighton Polytechnic in the United Kingdom. He has worked for Rockwell Automation as a technical support engineer before joining B&R. Both Joey and Sean will be available to answer questions after the presentation. So without further ado, I'm going to hand over the microphone to Joey.
My name is Joey Stubbs. I represent the Ethercat Technology Group for North America. The ETG is now the largest field bus trade organization in the world, with approaching 1,700 members, many device vendors, master vendors, and I/O vendors, as you will see in my upcoming slides. Just a brief overview of how Ethercat works. Ethercat has a very efficient Ethernet on-the-fly technology. Every slave device has a Ethercat slave controller chip built into it, and the purpose of this chip is to be able to insert and extract data as the data is coming by in the frame. So the master packets up all of the data for the entire network into one or multiple frames that are fired out, and they traverse through the entire network. So it's a raw Ethernet frame, and there's no routing of individual frames to individual slave nodes via active infrastructure. The process data size can be almost unlimited, up to 60 kilobytes for large firmware updates, things like that. Also, since it's a very efficient protocol, we can address down to an individual bit per slave device and have multiple scan rates on the same network. In addition, we can do asynchronous or event-driven communication. So within each of the slave devices is this Ethercat slave controller chip, whose job is to modify the frame that comes from the master with either reading out data into DPRAM or inserting data that's sitting in DPRAM ready to be added to the frame. So from the master perspective, it sends out a frame with output data and receives back a frame with input data, just as standard Ethernet. And as many of you know, it is the fastest industrial Ethernet field bus available today, although it's very efficient. So that's one of the things to keep in mind with Ethercat. Although it's very fast, that doesn't translate into higher cost. It also does not translate into higher processing needs at the master. So update times, some key ones perhaps, those especially today tuning in who do motion control. 100 servo axes, 8 bytes in and 8 bytes out for each axis, being able to do that in 100 microseconds. 1,000 digital I/O in 30 microseconds. And since it's can support such high update rates, we can even do some elementary oscilloscope functions, for instance, doing 200 16-bit analog channels at 20 kilohertz sampling rate. So as I mentioned, there is no active infrastructure such as switches, hubs, or routers. All of the routing of the frame is actually just an electrical signal that has a logical order that goes through the entire network. So when a master sends out a frame, whether that particular slave is addressed or not, the frame itself will traverse through the entire network. This allows us to do efficient slave-to-slave communication for things like our safety protocol, and also allows us to have asynchronous communication if a slave wishes to request a firmware update or has something to put onto the frame. It can request asynchronously, and therefore allows us more efficiency with the bandwidth. So from a master perspective, it sends out the frame, and this frame will traverse through the entire network. If there's nothing connected at the end of a segment, that frame will be turned around and course through the next segment of the network and continue traversing through the entire network. And at the end of going through all of the slaves, the frame will be returned to the master. So within the Ethercat frame, which is a standard Ethernet frame, it's a multicast or broadcast frame, has an Ethercat header, and then the remainder of the frame is divided up into what we call datagrams. So each datagram has a header and then has data packeted in it. So because we do not map via a field bus card back at the master, all of the mapping is done implicitly via the protocol. The master is actually telling the slaves where to find their data in the frame. So this alleviates a lot of the CPU usage for the master and frees up the CPU to be used for the job that you're trying to do, which is your application. So all of this communication from a slave perspective occurs in hardware. So there's no CPU stacks in each of the slaves that can get bogged down and slow down the rest of the network. So predicting the performance is extremely easy. And as I said before, there's no switches required or suggested or hubs or any other infrastructure. And there's outstanding diagnostic features with exact localization of where faults are, what the fault condition is, both from a physical cabling perspective and from a logical perspective if a device is not updating the RAM correctly or if you have CRC errors. And it's still 100% 802.3 Ethernet. So the master's job is to set up the logical process image in the RAM of the master to look exactly like the frame that's going to be sent out over the wire. And it only has to do this once at the beginning of the run. After that, it's all taken care of, and there's no more processing of having to worry about addresses. So one of the things that Ethercat does up front that makes life very simple later on.
I'm going to ask a quick question here. One of the attendees is questioning the yellow line. Is it a single Ethernet cable or two cables, one for each data direction?
It's a single cable, or it can be fiber optics. So it's a Cat5, Cat5e, or fiber optics. So physical layer, there's actually 3 physical layers, which I think I touch on in my slides here. So from a synchronization perspective, which is very important for motion control, Ethercat uses a distributed clock mechanism as opposed to IEEE 1588 or one of the other protocols. So each of the slave devices is able to measure the time difference between a frame going through and coming back very accurately. And it reports this back to the master, who can then, because the master knows what the topology looks like, can tabulate all of these delta t's along with the topology to calculate the propagation delay between any 2 slaves which have the distributed clock feature enabled. This allows us very easily to synchronize the entire network to a 64-bit clock, and then a very simple phase lock loop instruction, which is just one small instruction goes out that allows the slaves themselves to compare what they think the time is to what the actual system time is, and make corrections themselves through a drift compensation algorithm. So this allows us to synchronize the network not to the millisecond and not to the microsecond, but actually down into the nanosecond range. So this is a long-term scope view of 300, I think it's actually 302 nodes. So we're firing an, the first output of the first node and an output of the last node, and we see that we get a jitter of plus or minus 20 nanoseconds in this example. So very high ability to synchronize the network, even with jittering master frames. So for drive manufacturers and drive users, it's very nice that Ethercat is covered by two of the annexes of 61800. IEC 61800 is the electrical power drive specifications. So there's mapping of objects for CAN and automation, so the CIA 402 specification, and also for the Circo specification. So you can purchase drives from vendors that have both CAN open objects, CIA 402, or conformant to the Circo's IDN specifications. So there's a large variety of device vendors for drives. There's actually 90 different vendors currently, adding to them weekly. So 90 different drive manufacturers creating and selling Ethercat drives. And there's actually 120 different off-the-shelf master controllers. These aren't all motion controllers, but they are all Ethercat controllers, so they could be small embedded PLCs or full-blown robots or motion controllers. So you see some very large names there. This was from our latest booth at the SPS Drive Show in Nuremberg, Germany. We had one small PC running a network of 35 different axes from 24 different vendors, a combination of both steppers and servo drives, all running a synchronized program with the little wheels on the wall there. So I believe it was some kind of world record for different vendors, different drives on one network. For manufacturers of drives and for those who are benefiting from buying off-the-shelf drives, the ability to develop drives is very streamlined, that the slave sample code now contains the CIA 402 drive implementation and examples thereof. Also, the conformance test tool from the ETG for validating conformance to the Ethercat specification also has the ability to test that implementation of a CIA 402 drive. And for those device vendors, there is a CIA 402 drive implementation directive that allows them to easily determine which are the mandatory, which are the optional objects, and how to implement them into an Ethercat servo drive. So from a motion control perspective, there is lots going on with Ethercat, and we're adding to that every day. One of the things that was developed along with Ethercat is the Functional Safety over Ethercat, FSOE specification, which allows Ethercat to act as a carrier of a black channel safety protocol and allows you to distribute your safety devices along the Ethercat backbone using a standard PLC or PC architecture, along with lots of non-safety rated I/O. And then you have a safety logic controller out in the field, or multiples, and safety inputs and outputs that are linked logically to the safety logic. And one of the advantages of a safety protocol such as this is the ability to have drives that now we don't just drop the mains power and turn off the drive. Now we can actually command safe commands such as safe torque, safe direction, safe speed, and actually implement a logically safe implementation on a machine or a robot. So you can get some more information at ethercat.org website, or I believe that my contact information will be available on this presentation. So feel free to contact us with questions about Ethercat. And with that, I'll hand it back to Leslie.
Thank you, Joy. I appreciate that. Okay, now we're going to hear from Sean, and he's going to go over PowerLink and how that can be used in real-time control.
My name is Sean Neller. I'm Key Accounts Manager with B&R Industrial Automation. Just the connection between B&R and Ethernet PowerLink was originally the Ethernet PowerLink was developed by B&R, and later on it was formed into a group called the EPSG, the Ethernet PowerLink Standardization Group, and they really now control the direction of PowerLink worldwide. So as you already saw from Joey's presentation, it used to be that the networks were the slow part of any control environment, and were the limiting factor on any control applications that are being put together. Well, now that obviously isn't the case, and once again I'm clicking the mouse and hopefully everything's going to come up. So first of all, I want to go briefly over some of the network features of the Ethernet PowerLink. So 250 axes per segment, so you, along with standard what you expect from an Ethernet-based system. The additional nodes that you would normally see there are taken up by special nodes that we've reserved for future expansion, things like master nodes and everything on the network. Network updates of less than 400 microseconds with up to 250 nodes of networks. The number, the 400 microseconds, does vary, and maybe we'll talk about that a little bit later on, depending on the networks and the devices you've got on the network. I'll explain why that is in a subsequent slide. One of the interesting factors and one of the interesting things about Ethernet PowerLink is that you can download operating systems to all the devices and configuration modules to all the devices automatically from the control system. So, for example, if you had, we're talking about drives today, so if we had a drive out in the field that was faulty for some reason at an end user, for some reason someone would pour coffee in it or something, the drive can easily be swapped out, can be purchased from a local distributor or a local vendor, plugged into the system, and then the operating system would either be upgraded or downgraded depending on the application program, and all of the parameters and everything would automatically be transferred to the drive. This cuts out the need of the drive being shipped from a vendor to the OEM, and then later on and pre-configured, and then later on sent out to the user. So it reduces downtime on machines and systems. So very easy to swap out devices in the field, very easy to update devices in the field if you want to update to a newer version of the operating system, for example. I want to just explain briefly how the cycle on PowerLink works, a little bit different from the Ethercat examples you saw a moment ago. We have a managing node, master node, which starts the communications off. It sends out data, and everything that is sent out on the PowerLink network is broadcast. So everyone can hear everything that's sent out, and everyone can hear everybody else's replies. This is a great advantage to the PowerLink network. So when the master sends out details, it sends out information about I/O for individual nodes. It sends out all of the datas and speeds and set points maybe for individual drives, and then in sequence the standard cycle drives, we should see it change in a moment hopefully, there we go, the non-multiplex nodes reply in sequence, and then after they have replied, then the master once again sends out a request to the multiplexed control nodes, and then they would then reply in sequence. In this example we show just one multiplex control node, but this could be multiple devices, could be a number of devices sending back. After the multiplex nodes had actually replied, we would then get an asynchronous portion of the network for asynchronous data that you want to transmit across the network. For example, if you have HMIs or SCADA devices that may be working in an asynchronous fashion and not sending identical data every time, or indeed if you have a TCP/IP type computer that's connected through a bridge into the network and you're transmitting data on the network, this would be transmitted in the asynchronous portion of the frame. One of the things that is an advantage of PowerLink is, as you see here, we have a function called Crosstalk, which when the nodes are replying, other nodes can listen to the replied data. So, for example, if a master is transmitting access position, or it's transmitting speed information, velocity information, current information, back in a cyclic frame back to the master node, the slaves to that particular device can be listening and take that information, and then they can synchronize to that data. So they don't actually have to be transmitting data at the same rate as the master. The master could be transmitting data at a higher speed, and the slaves then could be listening, and then they could synchronize themselves to that master node. Of course, this information, when this is happening, doesn't have to actually pass through the master, because it's just information that's being broadcast. So we don't actually have any information flowing directly to the slave. It's just flowing back from the access back to the master node, and the slaves will then be listening to that, and then they would actually respond to that as and when they will. So obviously this process repeats, and the data that's being transmitted back from each of the masters would be transmitted at a higher rate than the data that's being transmitted back from the slaves. And so the slaves are then able to listen to that, and obviously do their control at a much higher rate than than their actual communication on the network. So in this particular example, of course, you will have some nodes that aren't transmitting data back all the time. They're just listening, and these are obviously called multiplex nodes. And here what we see, and I hope everyone can see the animation there, we see that during one cycle, the cyclic nodes are being transmitted back, but in subsequent cycles, the multiplex nodes are transmitting back. In this case, node number 2 is transmitting back in cycle 2, and then node number 3 would then transmit its information back in cycle 3. Once again, because all the information is broadcast from the system, from each node, all the other nodes can be listening at the same time. So even a master node or a cyclic node could be listening to a multiplex node when it sends its information back across the network. So just a little diagrammatic way of seeing this. Here we see in cycle 1 you would see maybe node 1, 2 and 3 transmitting cycle 1, and multiplex nodes would be in this case 4, 5 and 6. And in the next cycle, 7, 8 and 9 are being transmitted back, and in the final cycle there, cycle plus 2, 10 and 11 are being transmitted back. They don't even have to go in these sequences. You could do 4, 5, 6, then you could do 7, 8, 9, then you could do 4, 5, 6 again. So you can set the sequence in which data is being transmitted back from each node, and at what time nodes are listening and what time they're actually transmitting their information. Topology, well, this is 802.3 compliant, as we've already, as Joey mentioned in his system. So we can connect these in a daisy chain. All of the PowerLink nodes have 2 ports on them generally, so they have a little hub built into the units. Or we can have a star configuration. Or indeed we can connect the units in a ring. Now, use the actual devices that we use to do the star configurations, or even a bus configuration, could be hubs or switches or even wireless devices. The only restrictions on that is obviously if you were using, for example, a wireless device, and obviously the timeouts are much larger, and in a real-time environment probably wouldn't really be practical for doing real machine control. So you can freely mix and match any of these different topologies and put the system into any configuration you might want. So a combination of bus, star, daisy chain are all possible. You can put those all together. Also, in a ring configuration, it's also possible to have a redundant situation where we can go through slip rings, and we can detect a wire break in this situation and the network would still carry on functioning. We'd be able to detect a break in any part of the chain, and the network would still work, which is why it's ideal for going through slip rings, because then if you have a problem with one of the tracks on the slip ring, you're still going to get communication to your machine. You're going to get diagnostics to say you've got a problem, and then you'll be able to maintain the slip ring at a later date, but your machine won't actually be down until you actually go in and make the changes. Also, nodes can recover at any time, so if a node goes off of the network, it can be removed from the network. So for example, if you have a transfer machine where you want to take one of the stations of the transfer machine out of the network, you can remove the node from the network, everything will still function, and then you can put the node back in. In this case, of course, in a daisy chain situation, obviously if the hub is taken out, it wouldn't function anymore. But obviously in a star situation or something like that, you can pull out any node, and the node will then recover. The way that PowerLink is also configured is it's configured to work either in distributed or in centralized control. So in the case where you may have a controller in a system which has its standard, like a PLC, which would have its PLC scan at the top end, or a PC that's running at the top end, you could put the loop control, set point generation, velocity control down in the servo drive, or indeed the system can also function with the position control, set point generation in the main controller, and then the velocity and current loop could then be down in the motion control portion. This gives you flexibility. Either you can have different types of control at a lower end. It could be that you have some trigger positioning in there that you might want to be particularly precise. Then it takes completely out of the equation the main controller. The main controller isn't required to do any of that work, and all of that information can be disseminated from the main control down to the individual motion controllers or I/O systems. The other thing we do as well is we synchronize all the loops in the network, and this is why I mentioned the 400 microseconds. This is a standard BNR feature. It is not a feature of PowerLink. PowerLink, it is possible with PowerLink to go faster than the 400 microseconds that I stated at the beginning. In fact, we have run networks with PowerLink at sub 100 microseconds with over 240 axes in the system. In fact, the standard test we have done is 240 axes that runs at 65 microseconds. What we do in the network is we synchronize all the loops to minimize the round robin time or the jitter time across the entire network. So if, for example, if a particular, say an input came on a particular I/O rack, and then you wanted to go up to the controller, cycle in the controller, and then come back and turn on an output on the same rack, the round robin time is always deterministic. We can always determine exactly what the time is between the systems with minimum jitter on the system. Of course, it is also possible to set up the system so it doesn't synchronize all the loops, but in general that's what we do because it gives us the best control. Safety as well. There are safe motion devices which can also sit on the PowerLink network, and once again we have safe frames, redundant frames within the PowerLink packages, and obviously from that you can do eliminate all your emergency stops, your safety relays, and you can also eliminate all of your light guards and stuff like that wired directly back to safety relays and wiring them directly back to your control system. In this way they would come back into distributed I/O points, and then they could be transmitted across the network and then operate motion control with those features you see there, safe talk off, safe operating stop, safety stop, etc. So just looking at some of the devices that can go on to the Ethernet power link. Obviously distributed I/O, which you would expect, motion, which we've already spoken about, displays, HMIs, safety devices, safety I/O, which is directly put into the distributed I/O, safe motion products, variable frequency drives, other devices such as encoders, operator interfaces, PCI devices, diagnostics tools, etc. Also available is from SourceForge is Open PowerLink, where you can get the source code for EPL masters and EPL slaves to run on standard PCs. So you can use those as a master or a slave, a controlled node on the network. Also bridges are available, and bridges allow you to put a standard computer, connect a computer up or a device up, the TCP/IP device up to the bridge, and then that will transmit in the asynchronous frame of the power link and then be transmitted around the network. Okay, so basically when the multiplexing, the crosstalk, it allows fast communications without the management involvement. So for electronic gears, electronic cams, axis synchronization, CNC functions, you can connect, data can be read by slave axes or following axes very fast between the systems without the manager involvement. So you can have a very low-cost manager on the system, not very powerful manager, and you'd still get the same performance on the system. So it's very scalable in that respect. Also, this reduces the network cycle time you'd see on the system. Synchronizing loops and scans also allows us to sync the motion functions very accurately. And because we have a fixed scan, we don't have to measure the time like you saw on the Ethercat system. We know exactly how long it's going to take data to travel around the system. So we know exactly, because it's deterministic in that way, we know exactly what we have to do in the motion to allow for any delays in network traffic. Network safety, we mentioned as well. I/O devices. And the last couple of things, the network architecture with the cable redundancy, centralized distribution, local or distributed systems, and once again the I/O network systems. This I pointed out, it's 200 microseconds. As I say, it depends on the types of devices you're connecting up as to what network speed you're able to achieve. So thank you very much. Hand it back to Leslie.
Alrighty. Thank you, Sean. Okay, we have a couple of questions here, so I'm going to throw them out. One of the first ones that came in is, how open are these networks, especially in terms of source code? You did address safety networking, but maybe you want to go over it a little bit again, both of you.
Do you want to start, Joey?
Sure, Sean, thanks. So Ethercat is very open. It's an open open standard, IEC standard. It's also ISO and SEMI standard. From an implementer's perspective, there are master stacks for open source master stacks available for implementing your own controller. The slave devices, because we do things so high speed, you cannot do that in a slave stack. So it requires a hardware ASIC or FPGA to implement the protocol in the slave devices. But those are open for anybody to purchase through multiple sources: Beckhoff, Hilscher, Altera, Xilinx, and now Texas Instruments has their own chips that they've announced, which are attached to ARM processors.
Okay. As I mentioned, at SourceForge, you can get there's a PLC. There's a Ethernet PowerLink Open, which you can get from SourceForge, and if anyone contacts me through my email, they can get those. The source is actually on there for both for the masters and the slave nodes. Obviously, they would operate through standard Ethernet ports, and they wouldn't be dedicated Ethernet ports, but certainly fine for process control types environments and those types of controls. If you want very high speed, then in the same way as the Ethercat solution, we offer Fpga Solutions from Xilinx, from Altera, and you can purchase those directly from those companies, and XAT as well. And that we also offer a free stack for the FPGAs as well. So implementation is as low cost as possible. It's very open, and once again runs on the 802.3 IEEE 802.3 standards.
Okay. And
I hope that answers the question.
okay, for Sean, there's a question about, let's see, is there a web server for BNR controllers to show troubleshooting information, but will not disturb the controller code? What devices serves this, or what device serves these data?
Yeah, I'm not so sure if that's an Ethernet PowerLink question, but yeah, all of our controllers actually support a web server device. We also have a diagnostic feature in these which works across the PowerLink, gives you diagnostic information on the PowerLink. So all of our what we call our SG4 controllers support this feature. You can just connect up with a standard PC, and you can then do diagnostics across the PowerLink through that. Don't need any special code. It's all Internet Explorer.
Okay. And another one for you, Sean. This one is regarding, let's see, the 200 versus the 400 microsecond rate for PowerLink. Can you confirm this, and why the difference?
Yeah, I think I covered this a little bit in the presentation. For example, on our servo drives, the BNR servo drives, they have a 400 microsecond position loop update time, and so when we put those into a PowerLink situation, we would limit the PowerLink to that 400 microsecond update time. So we have a fixed cyclic time on the PowerLink. However, with other devices, it can be much faster than that. And as I already pointed out, sub 100 microseconds for up to 240 nodes is also possible as well.
Okay. This one is for Ethercat. Does the Ethercat process time increase with every added slave? By how much, since it's deterministic? And what is the maximum number of slaves on that network?
Yeah, the maximum number of slaves on the Ethercat network is 65,535. That can be any device, so it could be drives, it could be I/O, it could be whatever. What was the first part of that question, Leslie? I'm sorry.
Oops. Let's see. I can't find it. I deleted the question.
I think it was does it increase with each node that's added?
Oh, yeah.
Oh, yeah.
So there's a very, very tiny amount of delay that gets added when you add another slave node, but the overall effect is pretty negligible. The majority of the delay is actually from the frame itself. So as you, when you start your network, or if you start adding slaves, you actually don't have any impact until you reach the minimum IEEE 802.3 frame size, which is 84 bytes. So up to 84 bytes, it's pretty much a fixed amount of time, and after that you start lengthening the frame, which can impact your scan rate. But with Ethercat, and because it's full duplex, you don't have to wait for a frame to return before you send another frame, so you can actually pipeline multiple frames over the wire without waiting for the return frame. So you can actually get higher scan rate than just traditional polling. And the slaves also, depending on the implementation, they'll support oversampling at the slave device, both for inputs and outputs. So the interrupts at the device themselves can be tailored to either grab multiple samples or implement a train of outputs for ultra-short responses.
Okay. This one is for PowerLink. How is the bus topology different from daisy chain? And the questioner said that you showed a diagram for a bus.
The bus configuration, yeah, the bus configuration, it would really be done with hubs. So you'd, for example, you'd have maybe a 3-point hub would come in, and then you'd have a drop line from the from each of the hubs each time you want to do a bus. So it's really a similar thing to the star configuration. It would just be multiple hubs each time, and obviously each one of those lines could be 100 meters as well. So you know, which is the standard Ethernet lengths with the Cat5 cables, etc.
Okay.
I hope that answers the question.
And one more question for Sean. You mentioned some third-party products for PowerLink. What kinds of manufacturers offer compatible products?
Yeah, I'm glad you asked that, because I saw Joey put up a list of suppliers as well. Obviously in the drive area, I won't go through a huge list of names, but just some names that are familiar over here: Parker Hannifin, SEW, Yaskawa, ABB, Danaher. These guys are all have products that work on PowerLink. Also, there are other third-party products such as valve products, even encoders, and the encoders products would still come under our motion function, because they could be a master and other axes could be slaves and following those encoders. So people like TR and Posital, Pepper and Fuchs, these all have interfaces to PowerLink as well already.
Okay. That seems to be all the questions, but if anybody has any further questions, you see on your screen you have the email and phone numbers for both Sean and Joey, so you're welcome to send them any questions that you may like. You can send questions to me as well, and I'll forward them to either Sean or Joey as necessary. Thank you again, all of you, for attending. We appreciate your time, and this presentation will be emailed to everyone in a day or two, and it will also be available at www.designworldonline.com. And I have one other quick question that just slipped in, and it's, do you do robots and vision, either of you?
John, do you mind if I jump in there first?
Yeah, you go first.
Okay.
You go first. You've been doing it so far. So.
Well, you've had more questions, so.
Yeah, go on.
Ethercat is actually, that's one of the biggest growth areas is robotics. So humanoid robots, industrial robots. I think you saw KUKA, ABB are using Ethercat as robotics. Especially industrial robots work very well because Ethercat is hot connect, hot disconnect. So for an industrial robot, you can have the entire network be Ethercat and have end effectors that get attached or detached from the robot itself, and without having to go into any other operating mode. And it was robotics, and what was the other thing, Leslie, or was that it?
Vision.
Yeah, robotics and vision.
Yeah, National Instruments and Omron have vision products for Ethercat. I believe NI has vision products that are also Ethercat masters. So we anticipate there's going to be a lot more activity with vision because the Ethercat automation protocol was recently defined about 12 months ago, which is an upper level system which can also support gigabit or any other physical layer, so can support moving the big frames of data around. That's the problem with vision is people like to move the entire frame around instead of just triggering off of the logic. But depending on how you want to implement it, I think there'll be products for that soon.
Okay, yeah, KUKA, ABB, once again, these guys already have motion robotic products that will work on PowerLink, and BNR itself, we have controls for for robot controls built in for SCARA robots, etc., built into our control systems that work across the power link to robotic devices and robotic arms. Also, recently announced, Cognex announced a PowerLink interface for their camera series, and they should be releasing that soon. One of the strengths of PowerLink is that the large data frames that we can transmit across the network, so we don't have some of the restrictions that you've seen over on the Ethercat. So we can put some quite large data frames across there, and as I say, they'll be should be releasing that product very soon in the future. But the announcements have already been made on that.
Okay, thank you again to both Sean and Joey, and you got a little bit of competitive information there, but hopefully you'll all find it useful. Thank you to all the attendees too for joining us on this webinar. Again, it will be available in a day or two, and it will be on our Design World Online network as well. Thank you again.